Now we are going to look at voltage lines. Voltage lines are also called equipotential lines, and equipotential refers to the fact that you will have equal potential values, the same potential value on any line. Now we'll see why in a moment that these dashed red lines down here are going to be these voltage or equipotential lines, but just so we understand the equi part of it, if this dashed line that I just drew for you is a plus 12 volt equipotential line, then it's plus 12 everywhere along that line. Plus 12 volts, plus 12 volts, plus 12 volts, plus 12 volts, plus 12 volts. 12 volts everywhere. Well, the example that we're looking at here utilizes a uniform electric field. So before we get too involved with our voltage lines, let's go back and look at our electric field characteristics. E-field lines are drawn perpendicular to the surface of conductors, so we have that in there. That is true. Field lines are drawn closer together in stronger fields and further apart, so the blue lines are closer together in strong fields and further apart in weaker fields, and equally spaced for constant E. So that's what we're looking at here. E fields begin on positive and on negative, so we have a uniform electric field. Well, whether the electric field is constant or not, your understanding of the voltage lines that go with those fields will fundamentally, conceptually, come from our equation that delta V equals ED. Now, technically, that, of course, is only true if the electric field is uniform, but even if it's not uniform, I want you to use that relationship to understand how the electric field lines are going to be related to the voltage values at any point in space. So let's take a look at our voltage line characteristics. So let's go down here and look at this. So we are told that equipotential lines, voltage lines, are drawn so that the next line that we see, either to the right, to the left, the next line that we see will always equal the same voltage drop, and that is by convention. So anytime you see multiple lines, you certainly have to know the scale for the map. You have to be told what the voltage difference is between any two lines. For example, here it's a 2-volt voltage difference between lines. The 14 is just an arbitrary value we've assigned to the plus charge distribution. So we have a 2-volt voltage change, 14 to plus 12 to plus 10, and so on down to 0. Now, we will always understand the relationship between how many lines are drawn, the spacing between the lines, based on delta V equals ED. Why does that help us so much? Well, we know the delta V's have to be the same value from line to line. So that tells us that if the electric field is constant, if E is not changing, then D cannot change because the delta V has to remain the same. And that's exactly what we see here. The same distance, D, between the voltage lines. Now, if the electric field is small, right, so a weak electric field, then the D has to be big. So you'll see these dashed lines get further apart when we have weaker electric fields. And then, of course, if the electric field value, if the E value is big, so if it's a large electric field, then the D value will be small. They get closer together. Now, I do have down here, number 3, that these voltage lines are always perpendicular to the electric field lines, and we'll see mathematically why that is true on our next page of notes. But that is because the electric field lines will always give the direction of maximum decrease in voltage. So again, we'll see the mathematical reasoning behind that on our next page of notes. The last thing that I have that I want to cover with you on this page of notes is the definition of the electron volt, because that can also be confusing language. An electron volt is not voltage at all. It is energy. It is joules. So please make sure you get that down into your notes, right? It is not voltage, it is energy. And what energy is it? Well, that is pretty easy to understand, I think, in that it is the energy that a single electron acquires as it's accelerated through a 1 volt voltage difference. So remember, electrons are pulled backwards against electric fields, and for my example here, I did an initial kinetic energy equals 0, so it's released from rest. Change in kinetic energy equals negative the change in potential energy. Change in potential energy is Q delta V. The Q is the electron, negative 1.6 times 10 to the minus 19. Final minus initial, and voila, we get positive 1.6 times 10 to the minus 19 joules is the amount of kinetic energy that an electron acquires when it goes and is accelerated through that 1 volt voltage drop. So that is called 1 electron volt of energy. So 1 eV of energy equals 1.6 times 10 to the minus 19 joules. So box that up, and please remember that electron volt is energy, essentially joules, not voltage, and it's defined based on the fact that atomic and molecular physics, solid-state physicists work with electrons and protons, and they don't want to keep having to write down times 10 to the minus 19, so they just came up with this agreed-upon definition of a new unit for energy. So there you have that. We'll be doing more with these voltage and equipotential lines throughout the course, but hopefully this gives us a good start.